In this video, let us continue with more examples of higher derivatives. For example, if we had a function x minus 1 over x plus 2, how can we take more derivatives? Well, to start with, you can start with quotient rule, for example. So we'll have, just as usual, denominator squared. Then we have derivative of the top, which is 1, times the denominator, x plus 2, minus derivative of the bottom, which is 1, times x minus 1. So note how we can distribute the negative 1. X's will cancel, but we end up with 3 over x plus 2 squared. But a little bit later, we can rewrite it as the negative exponent. Because of the constant, we can do this, and we can also use chain rule for the other derivatives, which is a little bit easier than a quotient rule. So notice we can keep 3 as a constant, but to use chain rule, we bring negative 2 down. So it'll be 3 times negative 2, that's negative 6, times x plus 2, we reduce the exponent by 1 to the negative 3 power, times the derivative of the inside, which is just 1. So notice how we'll have negative 6 times x plus 2 to the negative 3rd power. That's the reduced version. We can keep doing it the same for third and fourth derivative, which is what we're trying to find. So negative 6 times negative 3, that's 18, times x plus 2 to the negative 4th power times 1. Or you can write it like this as a fraction with 4 in denominator, power of 4. And then 18 times negative 4, that's negative 72, times x plus 2 to the negative 5th power, or negative 72 over x plus 2 to the 5th power. So you can do that. And the same thing we can do with ln of x. Now notice you could keep using, well actually we keep rewriting it as negative exponent, and you can keep finding derivatives like that. Okay, now what can we do with a second derivative? One of the useful ways to use second derivative is to find out concavity, which determines the shape of the graph. That's really useful in the next section when we start talking about graphing. For example, a graph is concave up if it sort of looks like a U shape or a parabola shape or part of the U shape. Notice how the decreasing function, it could decrease or it could increase. So it's a U shape or part of it. Or concave down, which is upside down U, or like upside down parabola. It could be increasing, or it could also be decreasing in different ways. Inflection points are basically where f of x switches from concave up to concave down. So for example, it's very easy to see concavity intervals on the graph. Now take a look at this one. It's actually concave down all the way up to 2, 3. This point is actually labeled. And notice how it switches all of a sudden and it becomes concave up at 2, 3. Okay, so we're talking about concavity intervals on x interval only. So notice how I write this. F of x is concave down from negative infinity up to 2, and it's concave up from 2 to infinity. And the inflection point is 2, 3. This is where it switches concavity. Now, if we look at the equations, we can use second derivative to determine concavity. So this is, we can find concavity intervals and inflection points. So f of x is an inflection point at x equals, let's say, c, if the second derivative at that point is 0 and there is a switch sign in the number line. So if you draw a number line just like we did with first derivative, but you're plugging into the second derivative. So you're gonna pick some test points to plug in, and what you get is negative, let's say switches to positive, or positive switching to negative. That means you have an inflection point at that point. So we can do a quick example. So notice how I took the first derivative of the original function, then second derivative, then we can set that equal to 0. Notice how we can move 18 to the other side. And so negative 18 divided by negative 12, we'll get positive 3/2. So now I plot this on the number line. And again, I write second derivative, that's what we're going to plug in. So I picked 0 is always easier. And we know 2 is bigger than 3/2. So 0 I plugged in into negative 12x plus 18. Notice we'll get positive 18, which is positive. 2 we can plug in, so we get negative 24 plus 18. That will give us negative. So now we can tell the concavity. F of x is concave up from negative infinity to 3/2. F of x is concave down from 3/2 to infinity. And we also have an inflection point at 3/2. And how I got this fraction, I plugged it back into the original. And you can simply plug it in your calculator and turn it to a fraction if you wanted to also. Okay, or keep it as a decimal. We can also, instead of using first derivative, sometimes it's a little bit easier to use second derivative test for max or min. It just depends on the number line, how far apart they are, if you cannot pick, for example, integer points to test. So here is the idea. If x equals c is a critical number, we just take the first derivative, we find critical numbers, then if f of x has a max at x equals c, if the second derivative when we plug in this point is negative. And why it switches sign, it's negative, then it's a max. Well, it's concave down, so notice upside down U shape, it would have a max at that point. So I usually draw it, it should be very visual. And likewise, f of x has a min if second derivative at that point is positive, so we have concave up here, okay? And the test fails, or basically doesn't give us enough information if it's exactly 0. It could be an inflection point, but we still need to test it with the second derivative, so you may have to use first derivative test in that case. Okay, so here's a quick example. Find any extreme of the function. We have this cubic polynomial. You take the derivative of this, set it equal to 0. And notice how we find two critical points, x equals 0 and x equals 2/3. Now we're going to use second derivative test by finding second derivative. Derivative of 9x squared is 18x minus 6 for the 6x. And we're going to plug in into the second derivative. So notice I plugged in 0. And we got 18x minus 6, we got negative 6, and that's less than 0, that's negative. So we know we have a max because it's going to be concave down. Plugged in 2/3, 18 times 2/3, well, 18 divided by 3, that's 6, times 2 is 12, minus 6, it's going to give us positive 6, which is positive, so we have a min. And to find the y values, again, we'll plug it back into the original function. So I plugged in 0, I got 1. Plugged in 2/3, I got 5/9. Basically working out with fractions. And that's it.